To lift a massive, monolithic block of metal, brute force only goes so far. When a motor or a human armature strains directly against a load that exceeds its physical output, the resistance wins. This physical limitation is exactly why we build machines. In engineering, a machine is a device designed to overcome a large resistance by applying a smaller force. Lifting machines achieve this by enlarging the magnitude of the force being applied, or by changing the direction of that force to a more advantageous angle. When loads exceed direct human or motor capacity, we introduce a mechanical transformer to bridge the gap. Contrary to common belief, these machines do not reduce the total work required. The laws of physics and energy conservation are absolute. You cannot get more work out of a system than you put into it. Instead, simple machines operate on a strict geometric trade-off. To move a heavy object using a smaller force, you must apply that force over a correspondingly larger distance. This trade-off between distance, force, and energy loss is governed by three mathematical ratios that engineers use to evaluate any mechanical system. To understand how industrial weights are hoisted, we must quantify this trade-off by breaking a machine into two operational phases, the input and the output. This diagram outlines a lifting mechanism with two distinct sides. Output work is the physical result, measured by the weight lifted, W, and vertical distance traveled, X. Input work is the exerted energy, relying on the effort applied, P, and distance moved, Y. In a theoretical system, the two sides balance. The product of input effort and distance equals the product of output load and distance. Since work is force multiplied by distance, altering distances allows us to manipulate the required forces. To understand this geometry of motion, we temporarily ignore the load's weight and focus strictly on kinematics. This brings us to velocity ratio, defined as the effort distance, y, divided by the load distance, x. Because we divide one distance by another, the units cancel out. The velocity ratio is always expressed as a pure number. This ratio is a fixed geometric property. It is determined by the physical dimensions and routing of the pulleys, regardless of the lifted load. This pure number represents the mechanism's geometric limit, the exact factor by which the input distance is increased relative to the output. To move to the physics of power, we examine the actual forces, the heavy load pulling down, and the effort pulling the rope. This gives us mechanical advantage, the ratio of the weight lifted, W, to the effort applied, P. Mechanical advantage is the metric that operators feel in their hands. It quantifies how much easier the task has become. While velocity ratio describes the theoretical geometry of the system, mechanical advantage describes the physical reality of the machine's performance under load. For any lifting operation, maximizing this mechanical advantage is the primary objective. If a machine is perfectly designed, its mechanical advantage equals its velocity ratio. We would call this an ideal machine, operating at exactly 100% efficiency. Real-world machines face friction and material deformation, which always consume a portion of the input energy. This loss is measured by mechanical efficiency, the ratio of output to input, calculated by dividing mechanical advantage by velocity ratio. No machine operates at 100% efficiency. The mathematical gap between a system's velocity ratio and its actual mechanical advantage is the tax paid to friction. In this scenario, lifting a 1,000 Newton weight with 25 newtons of effort yields a mechanical advantage of 40. However, moving the load 0.1 meters requires pulling the rope 8 meters, giving a velocity ratio of 80. Dividing mechanical advantage by velocity ratio reveals a mechanical efficiency of 50%. While the machine successfully lifted the weight, half of the operator's total input work was lost to the internal friction of the system. These formulas govern simple levers and single pulleys, but modern engineering rarely relies on a single simple machine. To lift heavier loads, engineers design compound machines. This illustration shows how we layer multiple simple machines together to multiply the velocity ratio of the entire system. These configurations are standard in manufacturing, from differential wheel and axles to heavy-duty geared screw jacks. By mastering the mathematical ratios of distance and force, mechatronics engineers chain these simple mechanisms together, scaling fractional human effort into industrial power.
Thanks for watching and grow every day with just a bit of information. Like and subscribe for more content and learning.